coefficient? 0. The next one. The next one. The next one. What's the last one? 60. What's the order of the numerator?
2.
Change that to 2. What's the zeroth order term?
1.
Next one. 30. 9. Click to continue. We should say, you can see I mentioned that I have complex conjugate poles. You can say right here. Real part minus 0.15, imaginary part plus or minus 0.278. And of course I have the 0 that comes from the PI controller. That's also a GOL pole. That's it. Now, here I have two choices. I want to start from a low enough frequency so that the phase lag is going to be not 0 in this case. The PI controller would change the low frequency asymptote to be a different value. As a matter of fact, it makes it go to plus infinity. So, but something reasonable. So let's pick like 0.01 as minimum. And the high frequency must be high enough to have gone past minus 1/8. So one thing I can do is I can either iterate, give a minimum and maximum, see if I like the range that I have, and if I don't, expand it or contract it. Or I can try specific frequencies here. Let's look at some specific frequencies. If I give a very small frequency, like, well, 0.001, you can see here that the phase lag is close to minus 9. The asymptote, when you have integral action, the low frequency asymptote, instead of being 0, is minus 9. So we're definitely close to that asymptote. And I want a high enough frequency so the phase lag will go past minus 1/8, go below minus 1/8. So if I say yes to another frequency, so what was that I used before? 0.01 or 0.001?
1.001.
Okay, let's try 1 for it. 1, your phase lag you can say is minus 133. I need to go below minus 180. Let's try 5. 5, it has crossed to plus. It says plus because when you give a single frequency, it has to give you an inverse between minus 180 and plus 180. Only when you have the whole continuation, it continues becoming more and more negative, going towards minus infinity. That logic, of course, cannot happen if you give just a single frequency. So anyway, what did I use? 5? 5 was big enough. So we can say no to that. And absolutely don't make the mistake to say no here. Say yes. You want to see frequency response. And minimum, I'll use 0.0. Let's use 0.01. Maximum 5. 1600 points. So let's look at the volume. Here we go. So, what do? We can export it in Paint. We draw the line from minus 180 until I hit the phase lag, go up or down until I hit the amplitude ratio, go left. If I'm positive, above 0, unstable. If I was below 0, stable. Am I stable or unstable?
Stable?
I'm unstable.
I have no idea.
So, what's the procedure? Let's do it in Paint. I'll redraw the plot on it. Okay. so what I do is, let's pick a straight line. I go to minus 180. And I go left until I hit the phase line. Then I go up or down until I hit the log A output. And this frequency here is log omega C naught. This is the crossover frequency. The frequency at which phase lag is minus 180 is the crossover frequency. Do I have more than one crossover frequencies? No. I'm okay. And then at this crossover frequency, I check what is the log A output. So if that's positive, I'm unstable. It's above the zero. The log is above 0, which means AR is greater than 1. AR greater than 1 is the same as log above 0. So unstable.
How could you have more than one crossover?
If the plot happened to have been, okay, if it happened to be going down, then up again, and down again in that region.
But if that's the case, you would hit the first time.
You have three. You have three intersections. So in that case, it's not clear. If you have one intersection, it's clear. If you have three, it will be clear. What can you do to stabilize? Use lower control again. 3 is too high. What if I used 0.1? Let's use 0.3. Okay, 0.3 is right. The algebra will be divided by 10 on the numerator. So let's check if it will become stable if I decrease the magnitude of Kc from 3 to 0.3. So let's go back to the program. And not to mess up, click again body plot, because if you took it up, and now click go back. All right. So now we're going to change the B coefficient, the A coefficients, dividing everything by 10. So the 3 becomes 0.3. The 33 becomes 3.3. And the 90 becomes 9. And let's say no, let's use the same limits I used before, 0.01 as minimum and 5 as maximum, 1601. Let's see, did I go low enough? No, it's still unstable. It's still. Let's divide it by 100. Let's go 0.003. So let's go back. Let's change this. Divide by 100. No, not the big. Yes. So 0. Instead of 3, I'm making it 0.003. This will be for sure.
Professor,
Yeah.
for A1, you had 3 before you changed it instead of 0.3. Because when I used 0.3, it is below 0.
Oh, okay. Okay, 0.3. 0.3, 3.3.
You have 33.
Half 33.
Yeah, go back to A2.
Oh, no wonder. Oh, 33 points. Okay. Delete it all. Okay. 3.9. Okay. Let's check now. So 0.015, 1600. Yeah, I was surprised I saw so little change. Let's see. Okay. Yeah, that looks like it will do it. So that's how the plot changes. Notice the phase lag is not affected. The phase lag, as I'll explain, is not affected by the magnitude of Kc. Only the log AR. What we did is we moved down the log AR. Okay. So let's put it in paint. Draw the lines. So minus 180.
Is it always going to be the maximum? If it has a maximum?
No, just one. Nothing specific about one. Are we negative or not?
Yes.
We are negative. So reducing the gain from 3 to 0.3 would have stabilized the system.
See you on Wednesday.
Now see you Wednesday. So you got it's like half an hour early. Oh boy.
So I don't know what they want exactly, want zero, to make it so that zero.
I multiply, I changed the 3 to 0.3. I changed the controller gain, you see from 3 to 0.3. So when you change, here.
Let me get that.
So is the body stability criteria clear for everyone? Very straightforward to you.